All right. Just a sound check here to make sure everyone can hear me out there in Zoom land.
Sounds good.
Maybe. Okay, great. Yeah, I know we're going to have a few less people today because I think this class overlaps thermo, so we won't have quite as many participants. But let me get my Zoom going on my computer so I can see the chat and everything like that. Then we'll get started with lecture. So just hang tight for a second while we get going here. All right, there's the chat. Okay, this looks like it's recording. And like I said, we have a few less people today, but that's fine. The video will be posted for folks who couldn't make it during this special lecture. I was in a DOE meeting all day today talking about fuel cells and fuel cell membranes. Not 3D printing, but you know, sooner or later, we'll get DOE interested in 3D printing. All right. Are there any questions on the material or the homework? I've had a couple emails back and forth about people just with various questions, but I'm happy to sort out any issues here, anything that people want to discuss before we get started on the content for today. Okay, I assigned a new homework number 3. It requires you to look at some papers that I chose and to comment on them, or at least pick a paper and then do the assignment based on the papers that I put in the box folder. But if you're not happy with any of those papers, I just picked some of my favorites. Of course, you're welcome to pick your own paper, but I'd like to make sure that it's within the spirit of the assignment. So, you know, again, I want to see what insights you gather from the process and the material, and how the material and the process interact to get whatever additive structure people are interested in. And so take a look at the homework. It's due on Monday the 21st, so you have 2 weekends to work on it. So hopefully that shouldn't be too much of a time crunch in the next week and a half or so. So any questions before we get started? All right, let me share my screen and we'll switch over to the slides. All right, if you can still hear me, this is the slide I want to start on. So this is going back to lecture 2.5, and I go back to this one because this is one of the papers that you can read for your homework. But also, you should remember, if you're interested in the detailed engineering, so if you're new to materials, let's say you have a background in mechanical engineering or you have a background in fluid dynamics, you know, people are developing processing models for all these additive processes. We'll talk about some of them, and I'll briefly review some of them, but depending on your interest and your specialty, we'll go deeper into materials in the next couple lectures, but we'll always come back to what are the governing fundamentals of the process. And one of the fundamentals that we talked about in material extrusion AM is that the shear and the temperature distribution and the heating of the filament in this sort of arrangement is a lot different than the shear and the heating in traditional screw extrusion. And so part of the difference in traditionally manufactured parts is that the material processing is different and the geometry is different. And that all gets rolled up into why injection molded parts have different performance than additively manufactured parts. And so people are still analyzing how additive manufacturing is working in this context and trying to think about, you know, what are the molecular level phenomena that go into the part performance. And you'll see some of that in the papers that I assigned for homework number 3. So I just wanted to remind you, as we talk a lot about materials in the next couple lectures. We'll come back to the process fundamentals eventually. So again, if you have any questions, you can just chime in, unmute yourself, or just pop it in the chat. I'm taking a peek at the chat periodically on my computer, and so feel free to interrupt anytime. Let's see, last time we weren't on lecture 2.5, we were on lecture 3. And so last time we were talking a lot about different high temperature polymers and composites. So I want to talk about all these different polymers, and I'll talk about their properties and their chemical structure. And then really the properties lead us to thinking about where these materials are used in applications. And so we've talked a lot about PA11 and PA12 and different nylons. We talked a little bit about Ultem polyimides, and then some of the other high temperature thermoplastics, or we call these engineering polymers, whether it's a polycarbonate or whether it's a polyether sulfone or something else. And we're sort of climbing up the polymer performance pyramid. And so these polymers get more expensive, they get more difficult to process, but they give us better properties in whatever application we're interested in. And we ended up on these PEEK, or polyaryline ether ketone polymers. So A equals aryline, which is this aromatic or this benzene group. E equals ether. K equals ketone. So this is an ether bond. This is a ketone bond. And we're not going to have a polymer chemistry course here, but you should know some of these terms, because all these different materials, whether it's PE, KKK, which is ether, ketone, 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 or whether it's PEK, ether, ketone, or the traditional PEEK, ether, ether, ketone, and of course P stands for poly. There's a whole variety of these materials, and it turns out there's about 50 or 60 different types of ketones and sulfones and other things like that. And so you could go look into the literature from various polymer databases or other types of polymers or other types of polymer databases, and look up all the different materials that are possible. There's even a company in State College, Pennsylvania, right next to the UP campus, that specializes in these types of materials. So Polemics is the name of the company, and they do rotomolding and other types of molding of these high temperature polymers for oil and gas applications. So these are widespread engineering materials. They're about as expensive as it gets in terms of polymer materials, but they're also at the tip of the polymer performance pyramid. So these are valuable materials, and we would really like to bring them in to additive processes. And we'll talk about some of the ways in which these PEEK polymers are used in additive, especially when we get to powder bed fusion, because there's a whole biomedical suite of materials, especially skull implants, that are done using these polymers. So anyway, when we get back to talking about applications of PEEK, these are the types of polymers we're talking about. And we call this the polyether ketone family. So we have all the different mixtures of ethers and ketones. And so whether you're interested in buying materials from Dexmet or Michelman or Arkema also makes these, BASF makes PEEK. There's a lot of different places that you can buy these polemics. And so as you're investigating different materials, these all have very similar properties, and you can learn about a lot of the polymer properties from sources like this. So whether it's Stratasys and you want to figure out what polymers are used in a 900 MC, or if you look up MATWeb, you can find all the different grades and filled polymers. And properties. So if you type in nylon 6 in MATWeb, it will tell you all the different glass fillers that are available, what their general properties are, what their temperature resistance is, all sorts of things. If you're interested in Ultem, of course, SABIC has a lot of information on that. And so as you're looking for different polymers, different grades, if you're interested in different types of materials, you can go to these databases and find what's possible. Any questions on sort of polymer chemistry, polymer performance pyramid, sort of polymers in general? We're going to start talking about composites and filled polymers in this lecture, but does anyone have a polymer question that they want to ask now? All right, so like I said, we're going to start talking about composites. And composites, the way we're going to approach composites is basically polymers filled with something that's not a polymer. So there's lots of different ways to make composites. Fiberglass is a composite, even a laminated structure where you might glue rubber insulation to a metal panel. That's a type of architectural composite. Of course, concrete is a composite material because it's got aggregate and cement in it. But we're going to talk about composites primarily from the angle of a polymer with other stuff in it. And so when we think about integration of composites into a 3D printing process, we've talked a lot about what are some of the issues of putting polymers in 3D printing. But now that you think of composites, so polymers with particles in it, like this, for instance, so you might fill a polymer with carbon fiber, or you might fill a polymer with silica, or you might fill a polymer with metal particles. What are some of the issues now with integrating composites into an additive manufacturing process? People want to chime in or type it into the chat. I'm interested in what are some of the things that might crop up here? Don't forget to unmute yourself and chime in.
Might you have problems with melting?
So you could have, let's say, high viscosity with added filler. So in generally, the MFI goes down with particles. So if you have a polymer that's hard to process and you put particles in there, it's even going to get harder to process. So composites don't necessarily change the TG or the TM very much. Oh, hold on, my kid's texting me. Polymers don't change the TG or TM very much in composite systems, but the rheology changes a lot. So the melt flow index changes a lot with the melt flow index changes a lot with filler addition. And so again, viscosity, melt flow index, you know, we talked about the rheology needed to get good flow. That could be a real issue in composites. Any other ones that people can think of? Want to make sure both parts of the composite can, yeah. So how does filler, you want to open up your chat so you can see the comment from Locke, but he said, we want to make sure that both parts of the composite can withstand the 3D printing process. So how does filler move through the 3D printing process. So that's important if you want to use continuous fiber, or if you want to use a woven mat like this. You know, there aren't a lot of printing processes that can actually integrate that part of the composite into the process. So you have to think about that. Although I'll show you some ways that we use continuous fiber in this process. But if you want to use woven carbon fibers, the only way to do that is probably sheet lamination. And of course, that's a niche AM technique. Other issues. So maybe if we're interested in a composite where you have a nice distribution of fillers, you know, does the filler stay well dispersed during AM? So that'll be important, you know, is what you put in the composite to begin with, is that what you get out after all of your composite manufacturing is done? That's important. Any last issues here on how we integrate composites, or concerns that we have about composites in 3D printing? One other one that I'll put in here is how does the filler contribute to road adhesion and anisotropy? That's sort of the same as, does the filler stay well dispersed during AM? But if the filler segregates to the surface, or if the polymer segregates to the surface and the filler doesn't, that could affect road adhesion, making it better or worse. And if we have an anisotropic filler and we're doing AM, we might give very anisotropic parts. And so we need to be aware of that. And I'll show some examples of that as we go on talking about more composites. So any more comments on this slide, or any questions that people have or comments they want to make in terms of chiming in on what difficulties we might encounter as we try and do composite AM? All right, well, we'll keep going. So you should have a sense for polymers and what their properties are like so far in this class, even if you haven't studied polymers before. And so the next lecture or lecture and a half is really to give you a sense of composites as materials and how we integrate those composites into AM. And then we're going to talk about some AM issues again. So we're not quite done with melt processing yet. We still have to talk a lot about roads and things like that. But we'll come back to melt processing after we talk a little bit about composites. And then we'll move on to SLA and SLS and some other additive processes. But we're still going to be on melt processing for a little while, because melt processing is the dominant technology for shaping polymers right now. So the question is, how do you get this through a die if you want to do AM? So how do you get chopped carbon fiber? So this is chopped carbon fiber. This is woven carbon fiber mat. So this is in a carbon fiber composite. And so when you buy a golf club, or well, golf clubs are made using wound fiber, but tennis rackets or ping pong paddles or other things that are carbon fiber, or say a high performance part for your car or bicycle, you see that weaving of the carbon fiber. That's what this mat is, and it's impregnated with polymer and cured. You have high aspect ratio fibers right here. You might have unaligned chopped fiber, or we might call these whiskers. And so depending on how this road is processed, we might get alignment of that. And we need to think about, what does the matrix look like? This is generally the polymer. And in this case, it's a fiber, or this will be the filler. What is the distribution? What is the adhesion between the matrix and the filler? Those are all things that we care about in composites. And so we're going to talk about some of those issues so you can get oriented to composite materials, and then we'll bring it back to AM. So the aspect ratio of the fibers, or remember, every time I say fibers, I could mean filler, because these could be anisotropic particles like silica. They could be metal filler. They could be cellulose nano whiskers. They could be something else. They could be platelets like mica. And so we could have high aspect ratio or continuous fibers. We could have short fibers or filler, or low aspect ratio, or we could have something that's more like particles. But all of these things will really make a difference in the properties of the material. So depending, once we choose the polymer and the filler, then we need to think about aspect ratio, orientation, and aspect ratio is really a choice of material and how material changes during AM process, because we can break fibers as we're doing AM if we want to. And orientation really has to do with characteristics of AM process and alignment. So we'll talk a lot about how we get orientation in AM processes and why that might be good and why that might be bad. But you'll see that a lot of the concern, especially with something like material extrusion AM, is that orientation is built in as an intrinsic part of the process, and we'll continue to discuss that. Orientation is in a pure polymer road, but orientation is especially important in a composite. Even with short fibers, we can see effects of orientation, and we'll discuss that as we go on. So in order to make a composite, all you do is call a compounding company. So as we do this, this is usually called compounding. And that's done in something called a, well, here it's single screw extruder, but you could have a twin screw or compounding extruder. So you buy a polymer, and of course resin means polymer. You buy a filler, and you might put some other stuff in there like processing aids or plasticizers or additives. Turns out the polymer in a bottle of laundry detergent has about 10 or 15 different molecules in there because you need colorants, you need stabilizers, you need things that resist degradation, you need things that make the polymer opaque, crystallizing aids, all sorts of stuff. And so you do this compounding process, and then you extrude your composite out of your die, and we'll talk about what sizing is in a second. And then you cut it back up into plastic pellets, and so now you have composite feedstock. And of course, this is showing for plastic pellets, but you could take this and you could make it into filament if you want, or if you play your cards right, you can take this off as filament right here. But it turns out that some polymer companies make composites. So if you go to Sebec's webpage, you can buy composites. But also there's a lot of compounding companies. So in composite compounding, or sometimes these places are called polymer converters, where they make their own composites buying things off the shelf. So you can get a lot of custom composite materials made. And if you go, like I said, if you go to MatWeb, you know, there'll be lots of grades of nylon on MatWeb, so different melt flow indices, different characteristics of nylon 6, but there will be hundreds of different composites available. 5% chopped glass fiber, 10% chopped glass fiber, 30% chopped glass fiber, 20% carbon fiber, you know, silica filled, TiO2 filled at all the percents. And so making composites really expands the types of materials that are available. And in general, we'll talk about properties of composites, but in general, you make a composite in order to stiffen the material. And so lots of times composites are stiffer than polymers. And in some cases, they're less expensive because even though you have additional processing, if you're taking a really expensive polymer like PEEK and putting silica in there, which is inexpensive, you can get your material cost down. And so you'll see a lot of packaging materials are filled with what they call post-consumer content. Or you'll see commodity polymers like polyethylene and polypropylene will be filled with silica because it makes it cheaper. So this is not always true because carbon fiber is not inexpensive, but people make composites for lots of reasons. And one of them is to improve properties, but they can impact the cost as well. And we'll have an assignment talking about the composite effect, or why you would want to make a composite in the first place. So that'll be in the future. These are what compounding extruders look like. Sometimes you see what's called pre-preg. So this is pre-preg means polymer plus filler that is not cured. Let's get cured right. So you can have a thermosetting composite. And so this will be a thermosetting thermoset molding. Sometimes this is called compression molding. You don't really want to thermally extrude a thermoset because it's going to cross-link in the extruder, but you still use an extruder to pressurize this thermoset into a heated mold, and then you get a molded part. So you'll see pre-preg in the composite literature quite often, and that's a cross-linkable polymer that's not cross-linked yet. It's in its precursor form or pre-impregnated form. This is a compounding extruder where you can feed two things in. So you might put polymer in here. It goes down the barrel. And then once it's melted, you put the filler in here. And this thing disperses the filler in the polymer, and then you get a composite out the front end. And there's various ways that people do this. This is a multi-screw compounding extruder. That's pretty awesome, but that's a serious piece of equipment. And so you can see that you get a lot of mixing from that. This is just more diagram of the same thing. So the polymer industry is good at this. They're good at making composites, but the AM industry is not yet there in terms of making composite materials. So you can buy composite filaments, you can buy composite feedstocks, but if anyone has done a lot of material extrusion AM of composites, in this class, they'll know it's not easy. And because most polymer products that you buy out there are some kind of composite, really thinking about how you might want to AM composites and what it's going to take to AM composite materials is really important. So you can check out these diagrams if you want, but there's a lot known about composites generally in the polymer industry. Now we need to translate that knowledge to AM, and that's what people are working on. Okay, I'll pause here. If there are any questions, I'm happy to answer them as we spool up composites. We're going to talk about some more details of composite materials and how we might think about composites, but I'd be happy to take any questions right now. All right, let's keep going. So the AM industry knows that composites are important. This is a really nice article. These are some companies that are interested in composite materials, and you notice that there's not a lot of companies that really specialize in this, even though we can buy composite feedstocks. This is a real challenge for material extrusion AM for a number of reasons, and we'll talk about that. But you see, mostly it's chopped fiber or chopped and milled filler, which means it's just broken down into small pieces. There's only one bona fide company that does a lot of continuous fiber additive, and we'll talk about that in a sec, even though there's a couple of other machines out there that are really cool. But this is a real issue, because when you go buy a water ski boat, or you go buy a carbon fiber hood for your car, or you go buy, you know, some high performance glass or carbon fiber composite, it's usually woven glass or woven carbon fiber mat. However, this is really impossible to do in additive other than in sheet lamination. And it's even hard to get continuous fiber. So if you buy a golf club, that's a wound carbon fiber on a mandrel, or they make Boeing 787 fuselages using this carbon fiber winding process that I'll talk about as we get a little bit further on. But there's only one AM company that's really worked hard at this. However, if you want to AM wind turbine blades, or if you want to AM big composite structures, you're going to need to figure out how to integrate continuous carbon fiber or carbon fiber mats into your process. And that's hard to do. The other thing that we need to consider is that some of these ceramic composites or ceramic additive materials are composites. So these are generally in the realm of ceramic materials. So these are ceramic based filler. And in SLS, it's going to be plus, or it's a ceramic plus thermoplastic. because that's what you need in SLS, something that's thermally processed. And in SLA, it's going to be ceramic plus photopolymer. So I don't know if anyone has taken ceramic processing or made ceramics by slip casting or studied photoceramics, but these polymers now act as the binder. So ceramic particles plus binder, and you've probably heard of binder before in ceramic processing, and all we're doing is using the binder to accomplish some function in our additive process. And so binders is a well-known area for ceramic processing, and even there's an additive process called binder jetting, where you have a ceramic powder bed, and then you ink jet or jet in binder materials to do the additive. We'll talk a little bit about that, but this is an area where polymers can really influence the properties of the ceramic, and polymers can influence the final part properties. So these are both non-fired from 3D systems, and so these are not kilned or anything like that. In traditional ceramic processing, you'd cast your ceramic, you'd dry it, and then you'd kiln it to sinter the ceramic. These are unsintered parts where now they're being used as a ceramic polymer composite for higher hardness or better wear resistance or something like that. So it's a real interesting approach where you can get synergy between these different material classes to accomplish the additive shaping that you want. This thing right here is going to be really hard to make in a traditional ceramic process, but using an additive process where you have polymer plus ceramic, you can get the shaping done certainly with SLS or SLA, and you can make all these curved parts and other things like that shown right here that would just be really hard to do in ceramic processing. So you don't have the temperature resistance of the ceramic because the polymer is still in there, but you get some advantages from this type of composite system. And these are commercial materials that you can go buy from 3D systems in this case, although lots of different printer companies have these types of ceramic resins. Mark Forged is the continuous fiber integrated into thermoplastic. If you haven't looked at Mark Forged or you don't know what it is, they make some really cool stuff. And so these composites approach properties of aluminum, which is interesting because now you have light and strong materials that are even lighter and stronger than aluminum that you can 3D print. And so this is continuous carbon fiber, and it's sandwiched between layers of thermoplastic. This yellow stuff here, this is Kevlar fiber plus thermoplastic. And if you look very closely, you'll notice that you have layers of fiber and then layers of plastic. And so this is still an additive process where you have to build up the material layer by layer. And in Mark Forged system, you can't deposit both fiber and plastic in exactly the same place. And so you get these roads that are either carbon fiber or they're plastic. And within a layer, you just need to decide what the distribution of those two are. And so this does present some constraints because notice you can't get fibers going this direction in the part. Whereas if you have a woven composite, or if you've ever looked at a bike frame, a carbon bike frame that's not finished, you can see the composite fibers going in all different directions, and that's what gives it the strength. So the fibers are the high modulus part of this, and so they're very strong when you pull on the fiber in the long direction, but the matrix now provides the adhesion between fibers. And so a composite material might be strong or high modulus along fiber direction. But it's up to the plastic or the matrix controls modulus in, let's say, perpendicular direction to fibers. Sorry, that's a little tight there on the writing, but if you're listening to the lecture and looking at the slides, you can get the gist. So anyway, that's why in a carbon fiber mat, you have fibers pointed in all different directions in order to get high modulus in all different directions of the mat. But for the Mark Forge system, you're only getting high modulus in one direction and you're not getting high modulus in the other. So there's still some room for improvement here where how do you get reinforcement across layers? And that's a real conundrum. There's a paper in box for homework number 3 talking about how you might glue together layers to get high strength parts. And so you can read that one if you're interested in that. And there's one real cool company out there. I think they're still in business, but they're called Impossible Objects. And so they have this process called composite-based additive manufacturing. And so they have a really nice video, and this is sheet lamination AM. So like I said, when we started off the class, we're not going to talk a lot about sheet lamination other than just mentioning it. It's not necessarily a mainstream AM process. And so if you want to learn more about sheet lamination, or you want to talk about how you might make carbon fiber mat plus polymers. So these are basically carbon fiber paper plus polymer binder. You can check out Impossible Objects videos, or you can look at Sheet Lamination AM on YouTube. And there's some really interesting things there. You can buy a lot of carbon papers, it turns out. And then the key is, how do you integrate the polymer into that and get the material all set up for cutting out the sheets and then bonding and sintering them together. So this is something that you can investigate on your own if you're interested in sheet lamination AM, but I wanted to make sure it was there and represented. Arevo Labs has really worked hard on composites, and so they have a bunch of different polyairylene ether ketones and peaks and some other types of polymers that are integrated with carbon fiber, carbon nanotubes, glass fibers, and they have really nice demonstration parts, so you can check out this company. And we'll talk more about the details of composites, but this is one of the companies that's trying to bring composite materials AM to oil and gas, aerospace, and medical, medical, high-end jigs and fixtures, surgical tools. So these are all high value applications where you can really justify the use of AM and justify these exotic materials. Okay, we'll pause here for a minute. Are there any questions in general about composites? Or I just ran through a couple of real world examples here. We're going to talk in detail about what composite materials are, what exactly is happening in this sort of diagram where you have filler and matrix. But before we get into the weeds of composite materials and some of the things we need to consider, I wanted to pause and just see if there are any comments or anything that people want to bring up about composite materials in general, or AM of composite materials in general. All right, well, let's keep going. There's a lot of good composite stuff to talk about. And one of those good composite things to talk about is BAM, or Big Area Additive Manufacturing. And so remember, we briefly touched on BAM, and we'll look at a couple of BAM case studies because there's interesting things going on in this material extrusion AM process. But remember, this is a screw extruder. It's tipped on its side. This is a large polymer bead on the order of something like 0.5 to 1 inch bead. So it's a big piece of polymer coming out of there. And this material is black. And so this is carbon fiber filled ABS, I think. This is one of the grades of ABS that you can buy. And so ABS is a good engineering polymer, and then you fill it with carbon fiber, and it's stiff enough that you can make these large scale structures. And of course, this whole thing is like, or the scale bar on this is something like 4 feet or something like that. So composite materials have really played a role in the development of BAM, or making big structures. And we'll talk about why they use composites for this specific application versus just using unfilled ABS or using polycarbonate or something like that. And of course, here is the Strati. That's the name of the car for layer in Italian. But no one really wants to buy a car that looks like this. They want to buy a car that looks like this. And so this is 3D printed and surface finished. So this is no post-processing. You know, some people might like this look, but that's not what folks are used to in their automobile. And so 3D or post-processing is where the magic happens for additive manufacturing. And so there's been a lot of developments of how do you surface finish something that starts off very layered and in some cases very ugly in terms of the resolution, and get something that looks like a car that people want to spend money on. Or at least something that they're used to. And so a lot of the details of some of these large scale additive processes are in the surface finish and how that's applied and how durable it is. Another way that you can do this large scale additive is by using, rather than, we'll call this a gantry, and so a gantry system is X, Y, Z Cartesian coordinates. So you can move in the XY plane, you can move in the Z plane. And so I know you've been watching those MakerBot videos on YouTube trying to figure out you know, what your favorite 3D printing process is. And so a MakerBot is a gantry-like system where it moves in the XY plane and then moves in the Z plane to build up the layers. And you can see that here. With a robot arm like this, this is not confined to just XY plane and Z movement. So this robot, of course, is one of the welding style robot from automotive that can move in all dimensions, and you could have a 5-axis or a 7-axis robot if you want. And so you can have much more sophisticated extrusion patterns with this type of printing. We won't talk about the details of the design or the details of the machines necessarily. There are other classes in the AMD program if you're interested in design or interested in printing technology. But this is one of the options where you can have your BAM type extruder. So again, this is a screw extruder. And now you have freedom of movement for building up your part. One of the things that comes up when you're doing extrusion like this is that your extrusion bead or your road looks something like this right here. So this is 4 roads. 1, 2, 3, 4. And how this would be printed, it'd be printed in 1 layer here, and then 1 and 2 would be printed on top of 3 and 4. And the result is a micrograph that looks like this. So this is a bundle of roads. And the key part about this is that there's gaps in the middle. Let me highlight that so you can see it. Oops. That's too thick. Sorry, let me get this together here. And so we'll talk about that in a little bit of detail as we talk about building structures out of these roads. But the adhesion of these roads and how they're put together in the part, you can see in this diagram right here where they start and stop roads, how they do the framing of the part here versus this is just back and forth extrusion right here. You know, how they make these step edges. These are all important aspects of the design of the part from these sort of fundamental units. And there's some things that we can do to try and improve adhesion between roads or to try and get things compacted in such a way that we have as little defects as possible. So we'll talk in detail about this later, but there are both processing tricks and also perhaps some material tricks that we can use to mitigate this road adhesion issue. And this only gets worse and worse when you have composite materials, because you can imagine when you put fibers in here, if the fibers don't want to stick together, there will be more and more issues. Okay, the one cool continuous fiber printer is this thing that they call Mongoose. And so we talked about Mark Forged, which is a very small scale printer. You see this shoe bed here. A Mark Forged printer is like maybe a couple feet by a couple feet. This Mongoose, this is a person right here. This is a mandrel for a wind mill blade. And this big machine, I'm not going to run the video, but you can take a look at it in your own time. This big machine is laying down continuous carbon fiber or doing automated fiber placement at large scale. So if you need wind turbine blades, aircraft, wings, etc. If you need big stuff, this is the type of machine that they're working on now. And so you can call up Ingersoll Rand and ask them for one of their automated fiber placement 3D printing. You notice this is on a curved surface, so it's not yet free form, but it's getting there in terms of being able to three-dimensionally build up these big continuous fiber composite structures. So that's cool. You can check out that video if you want. So getting back to other applications of composites, this is a really nice paper right here from Professor Lewis's group. So Jennifer Lewis is a name that you want to know. She's at Harvard. She studied as a ceramist and as a member of the American Ceramic Society. And so she started in material science and ceramic processing and was able to leverage that into being one of the most famous 3D printing researchers in the world. And what she does is she uses her materials processing knowledge to leverage new structures in additive. So in this paper right here, what they demonstrated was this ink composite printing. And so this is still material extrusion AM, but sometimes this is called direct ink writing or ink printing or something like that. So you're still extruding material, but you're not doing thermal extrusion of a thermoplastic. You have some sort of liquid ink where the solvent evaporates and the ink has a high enough viscosity that it doesn't flow right away. But this is a really cool picture. If you want to read this whole paper, you're welcome to, because they're doing some cool stuff. And we'll talk about a little bit about this when we talk about 4D printing. But this ink does a really cool thing. So this is an isotropic mixture with elongated filler. And these are cellulose nanowhiskers in this example, I think. And so this isotropic mixture comes through the print head, but the filler aligns during printing Let me start again here. Filler aligns during printing due to shear. So you know, as you pump a fluid through an orifice, in this case, this is a die, and so this is, we know, probably about 300 microns or so. These elongated fillers align in the road, and so now we have aligned filler in road. And as this filler is mechanically stressed, as this filler in this paper is going to swell, you see different effects because of that alignment. So this is a really nice way to process a composite material because it's an ink, so you can maintain fluidity or lower the viscosity by ink formulation and still get the composite material you want. Now, this does have the disadvantage that you can't print structures that are very high because you need high viscosity ink to do that, and not lots of inks are highly viscous. But you also have solvents you have to deal with, you have ink stability issues you have to deal with, and so there isn't a lot of industrial ink printing except in bioprinting. And so bioprinting uses a lot of inks. Also in, say, printed electronics, they use inks as well. But you're not going to print a airplane wing using inks, or you're not going to print a tennis racket using inks, just because there are other disadvantages of dealing with these ink materials. But if you're interested in small scale structures, or you're interested in electronics. Let me say electronics. They use a lot of inks. You can put cells in these inks, and so the cells can live through the material extrusion AM process. So if you're interested in sort of the biotechnology printing or organ printing or biomedical printing, this is something that you might want to take a look at. And this is just material extrusion AM that's done in a different regime. Any questions on this so far? Any comments that people want to bring up in the last 15 minutes or so of lecture? All right, we'll keep going here. So when we make a composite, I mean, there's reasons that people make the composites that they make, whether it's for cost or properties or something else. But oftentimes you see this really interesting phenomenon called the composite effect, where if you look at, in this case, some property, this is fracture toughness, but this is property of interest. And as a function of the particle volume fraction, so this is how many particles you're putting in the composite. And so in this case, it's alumina trihydrate powder. So this is our filler. And it's in epoxy resin. So that's our matrix. So with a particle volume fraction of 30%, this would be 70% epoxy, because our volume fractions have to add up to 1, and this is the 2-component mixture. But this composite effect means that you get better properties by mixing the two materials than you can get from either material. So epoxies have a certain fracture toughness, so this is pure epoxy. Epoxy is just a thermosetting polymer. So the pure epoxy has a certain fracture toughness. And of course, the fracture toughness of this inorganic is going to be very low. So inorganic has very low fracture toughness. And so this composite effect means that you get better fracture toughness. Well, let's say higher. Higher fracture toughness from mixture. And so this synergism or this additive benefit that you get from mixing the materials is what people are looking for in fracture toughness. Because if you just had a line connecting the pure epoxy fracture toughness and the alumina fracture toughness, you know, this would be just linear mixing. And that's not very interesting because it's very easy to predict. But this composite effect is what people are looking for. And this is why fiberglass exists, or this is why carbon fiber composites exist, because you can't get the properties using just glass fibers or carbon fibers, and you need to have this mixture of both the polymer or the toughening agent or something that can absorb the energy, and the thing that provides the strength, which is the inorganic material or the carbon fiber or the glass. And so there's a lot of examples of this composite effect in the literature where you're looking for some synergy between the two materials that you integrate into the composite, whether it's conductivity or whether it's toughness, which you often see, or whether it's something else. This is why people make composites. So if you're confused about composite materials and why you might want them, you know, certainly higher strength is important, or in some cases, ease of processing, but also this composite effect is important as you start to think about how you might want to specify a material for the application you're interested in. And there's a lot of cool examples out there in the research literature. So this is a research paper right here. This is not a research paper. This is people trying to make wind turbine blades or aircraft wings. You know, that's really important. But there's a lot of cool demonstrations of composites that are out there in the research literature. And so this is one where they made what's called bouncy bone, which is really interesting. But this is a flexible bone scaffold, where we know bones are hard, or hydroxyapatite is a hard ceramic material. But in order to 3D print that bone graft, and in order to get it integrated into the body, they needed to add some flexibility. And so they made a composite material with hydroxyapatite and rubber in this case, in order to develop both the 3D printed structure that you see here, but also give the material some give. So you can check out that press release or that video in your own studying. But if you're interested in biomedical applications, this is where bioprinting really shines, because you can make all sorts of different composites that you couldn't make otherwise. This is a cool composite material, and so there's lots of SLA composite resins. Sometimes these are called ceramic resins, as I mentioned. And we'll talk about SLA from the polymer point of view later on in the semester, but a lot of these ceramic resins are just composites. And of course, you could take this composite material and you can kiln it or sinter it and make a sintered ceramic out of them. But a lot of times these ceramic resins are useful on their own for wear resistance, for other types of applications that you might be interested in. So I just wanted to bring that out as well. And this is a really cool demonstration of a polymer oxide and then metal composite. So this is a 3D printed oxide object. So this is rust plus binder. And so they make this iron oxide that's 3D printed into this lattice. And then if you reduce an oxide under hydrogen and at high temperature, you get something that's a metal. So we know that you can 3D print metal parts. So there's lots of metal printers around. You can do powder bed fusion or directed energy deposition of metals or something like that. But now this is a way to take oxides plus polymer binder. This is done using direct ink writing or material extrusion AM, and then you can reduce that to get whatever metal piece that you're interested in. And this is a really cool paper. If you want to check it out, here's the reference. And this is just showing some of the different oxides, whether it's iron oxide or nickel oxide or copper oxide, how you might reduce it to a metal, and what these inks look like that you can now integrate into your material extrusion AM process, something that looks just like this. So any questions on composite materials, any points of interest that people want to bring up in terms of the world of composites? Because we've talked a lot about polymers and the properties of polymers and the glass transition temperature of polymers. We're going to talk about photopolymerization of polymers as we go forward. And so polymers in all of these cases are still serving as the matrix. So we need to take into account the viscosity. We need to take into account the TG or TM if we're doing a thermal process. But now we're adding particles, which adds a lot of functionality to the material, but also might add some headaches in terms of processing. So does anyone have any comments or questions about composite additive or different sorts of composites that you might run into? All right, we have just 5 minutes left, and so I'm gonna just show a couple more slides. But this is, if you're interested in composite AM, there's lots of resources out there. And so depending on what type of homework assignments you want to do and what you want to learn as the semester goes forward, I encourage you to both consider polymer-based AM, but also moving towards composite AM, because that's certainly where the field is moving in terms of new materials and additive manufacturing. And there's a lot of papers out there for you to check out. So we'll just take a look at the next lecture, which I think is lecture 3.5, right here. So lecture 3.5 is on the box folder. Make sure you keep up with box. And so we'll just take a look at this one to start the idea. And I want to talk about what composite materials are from a detailed perspective. So we've talked about polymers from a detailed perspective and the properties of polymers and chemical structures of polymers. And so I want to talk about composites in the same vein. And the key part about composites is we know that there's a fiber, or you know that this is also filler. And we know that there's a matrix. In our case, it's going to be a polymer. Of course, there are other types of composites out there, like ceramic matrix composite, a CMC, or there's carbon-carbon composites, things like that. There's metal ceramic composites. We're going to talk about polymer based composites. So the polymer is going to be the matrix. The filler could be glass, ceramic, carbon fiber, etc., whatever we want, cellulose. And so the key part about making a composite is volume fraction, of filler and polymer. If you go back, well, let me see if I can go back quickly here, but if you go back to lecture 3 where we just came from, you notice that dialing in that volume fraction is really important. So when we talk about the composite effect, you really need to be able to dial in what the volume fraction is of the particle. And of course, when you make composites, you might make it in weight fraction or something like that, because mass is a lot easier to formulate than formulating to volume, but you just need to know the density, or you need some analysis technique to determine the volume fraction. But the volume fraction is what matters, because we're making a three-dimensional material. So volume is important. So how do you dial in the volume fraction? And then this issue that we haven't talked about quite yet, but we're going to talk about in this slide right now, is the volume fractions of filler and polymer, and then the interphase. And that's a little bit of an old term. Now we just might say interface between filler and polymer. In the composites literature, they call this the interphase because the properties of this coating, or the properties of this shell between the matrix and the filler, could be different than either the matrix or the fiber. And so this interphase doesn't necessarily have to be 1 or 2 nanometers just at the interface. It could be some other chemistry in there. It could be some other polymer in there. There could be something else going on to create this bond now between the matrix and the fiber. And so that's where this term interphase comes from, is that the properties of this glue, if you will, between the matrix and the fiber are really important for considering the strength of this composite. Because of course, if this is a fiber-based composite, so if our fiber is moving in this direction. Of course, the fiber again is going to control the modulus like this. But if we stress the composite in this direction, it's really up to the interphase to hold everything together and to give us strength between fiber particles, or between fibers, or between particles. So this is where we'll end up today. And I encourage you to think about this picture and to think about all different sorts of anisotropy and aspect ratio, and perhaps even chemistry, if you want to talk about chemistry that could go into this. And we're going to talk about how to make composites out of a lot of the different polymers that we've discussed. And then we're going to go back to the details of AM and how the AM process plays after we talk a little bit about the materials. So any final questions here to end on, either in the chat or in the, you can just unmute yourself and ask. All right, well, thank you for hanging in there with me on this late lecture. And so I'm available for office hours on Zoom, and we'll pick this up next week. And I think depending on what happens with classes, we're either going to be fully online, but if we can get through this hump after a couple of weeks and the cases start going down, we're going to have a couple of in-class lectures, because I think that'll just make it easier for everyone. And so we're aiming to have in-class starting in late September in a couple weeks. We just need to get over the Labor Day hump and see how things go. So anyway, I'd appreciate any comments if people want to send me, and I'm available for office hours. Otherwise, I will see you next time. And don't forget about homework number 3. You can do some reading. Thank you very much.
Thank you.
Thank you.
Thank you.